Welcome to Fundamentals of Artificial Intelligence. In today's lecture, we will look at constraint satisfaction problems. Constraint satisfaction is another way of solving problems in AI, where the main idea is to get to the goal state by satisfying a group of constraints. Many problems can be posed as constraint satisfaction problems, and off-the-shelf algorithms or constraint satisfaction problem solvers could then be used to get to the solution. While we were doing state space search, we explored the idea that problems can be solved by searching in a space of states. In such a situation, these states can be evaluated by domain-specific heuristics, and we tested to see whether they are goal states or not. Most of these states that we explored or we have looked at in problem solving as state space search, we can think of each state as a black box, which is assessed only by problem-specific routines: the successor function, the heuristic function, and the goal test. In contrast to that, in constraint satisfaction problems, we examine problems whose states and the goal test itself conform to standard and structured representation. Such a representation then allows search algorithms to be defined that take advantage of the structure of the states and then use general purpose rather than problem-specific heuristics to enable solution of large problems. Formally, a constraint satisfaction problem is a three-tuple: the set of variables. Each variable has a non-empty domain of possible values. A set of domains. Simplest kind of CSP involves variables that are discrete and have finite domains. Then we have a set of constraints. Each constraint is a pair. S1 is called the scope of the constraint and involves some subset of the variables. Ri specifies allowable combination of values for that subset. A state of the problem is defined by an assignment of values to some or all of the variables. A solution to a CSP is a complete assignment that satisfies all the constraints. A complete assignment is one in which every variable is mentioned, and an assignment is said to be legal or consistent if it does not violate any constraint. A solution is a consistent, complete assignment. Now let us look at a very popular problem from AI that uses constraint satisfaction problem solving technique: the n-queens problem. The n-queens problem is a problem of placing n chess queens on a n cross n chessboard so that no two queens threaten each other. For example, if we are talking of the 4 queens problem, we have 4 queens to be placed on a 4 cross 4 board, and we will mark these variables as x1, x2, x3, x4, and we have 1, 2, 3, 4, the different rows. Now, how do you specify constraints in such a scenario is that the constraints could be explicitly mentioned. Like if we start with a queen here and look for what could be the position of the second queen, so we will specify a constraint between 1 and 2, then a queen cannot be here, a queen cannot be here, but we can place a queen here. So that is what we are looking for, and therefore a constraint that says 1 and 3 is satisfied between 1 and the first and the second queen could be explicitly stated. So we have 1 and 3 here. Similarly, we could include 1 and 4, and then we could think of the second row for the first queen, and then the positions that could be possible is also not this, as the only position that would be possible is this. So, we could explicitly state that and include 2, 4 here. We could then think of going for the third one, in which case this also is not possible. The only possibility in the third case is having a queen there, and therefore, we would explicitly include 3, 1 to be there in the set of R, 1, 2. Here 1 and 2 refers to the first and the second queen, a relationship between them. Thereafter, we could look at the fourth row and see that these possibilities do not exist, that I cannot have a second queen here, I cannot have a second queen here, but I could have a second queen at 4, 2, which is marked there, and I could have a second queen at 4, 1, which is marked here. So, as we see here, we could state the constraints that I want between the first and the second queen as an explicit list, and this list is the list of allowable values between the first and the second queen. Similarly, I could look for values that would be possible between the first and the third, the first and the fourth, the second and the third, the second and the fourth, and the third and the fourth variables of these 4 queens problem. An assignment A bar over a scope S satisfies a constraint C if Si is a subset of S. That means that every variable in the constraint has a value, and a projection of that assignment over this scope is a subset of Ri. Now, we need to take a minute and try to understand what we mean by a projection of the assignment. So, let us go back and look at our 4 queens problem once again. We could have a queen at the first position. The second queen that I can place is definitely either this or this. So, I could place at 4, and the other queen now at position second for the variable x3 is what I can place. So, this assignment could be written as 1, 4, 2. Now, if you look at this assignment and if you look at the constraints that I was talking of and look at the queen 1 and the queen 2, then I could see that I have 1, 4, which is a possibility included in R1, 2. Similarly, if I had written the other constraints, I could have seen that I could have covered the possibility of having 4, 2 between 2 and 3 as well. An assignment is said to be consistent if it satisfies constraints in its scope. Like in the previous example that we were looking at, where I had an assignment of 1, 4, 2 for 3 queens placed on a 4 cross 4 grid, I could see that it satisfies the constraints, and therefore that assignment is said to be consistent. An assignment that does not violate any constraint is called a consistent or legal assignment. Now, this is interesting to note here that consistent assignments may not lead to a solution. Let us look back at this example one more time. We have queen at this position, which is perfectly okay with queen at 4 for x2 and queen at 2 for x3. But when we want to have a queen for the fourth variable, we are unable to have a queen here, we are unable to have a queen at the second location, neither in the third row nor in the fourth row. So, we are not able to arrive at a solution even if initially this assignment up to the third queen was consistent. Such an assignment is called a partial assignment or a partial solution. A partial assignment is one that is an assignment only to a subset of the variables. In this case, we could assign only up to x3 and we could not do for x4. We look at another example from constraint satisfaction problems called the map coloring problem, which is about coloring each region of a map in such a way that no neighboring regions have the same color. So here, if you notice, we have 1, 2, 3, 4, 5, 6, 7 variables, and let us say we are interested in coloring them in either of 3 colors. So we would have a domain of 3, red, green and blue. Now if we look at what is the constraint for this problem, the constraint for this problem is that any 2 adjacent regions must have different colors. So if you look at the first 2, let us say this is 1 and this is 2, the possibilities could be that I could have red green or red blue or green red or green blue, blue red or blue green. Now this is how explicitly we could state the constraints, or we could state what is allowed and the rest of the things are not allowed in mapping the regions 1 and 2, map coloring them 1 and 2. So here is a solution for the map coloring problem where we could have every region colored different. We will come back to this in our course of discussion today. Now depending on the types of variables, we could have varieties of constraint satisfaction problems. The most common of them are the ones with discrete variables. So they have finite domains. The Boolean CSPs, including the Boolean satisfiability problems, are of this nature. We have infinite domains, domains that have integers, strings, etc. For example, the job scheduling. They need a constraint language, and linear constraints are solvable, nonlinear are undecidable. Then we have continuous variable constraint satisfaction problems, where for example the start end times for the Hubble telescope observation. Linear constraints are solvable in polynomial time for such CSPs. Varieties of constraints may be possible. We may have unary constraints, constraints that involve a single variable, or we may have binary constraints, constraints that involve pair of variables. For example, here I have a constraint between x and y, and the sum of x plus y must be less than 6. Binary constraints can be represented by constraint graph. Then we could have higher order constraints, constraints over 3 or more variables. Now it is interesting to note that we can convert any constraint into a set of binary constraints. They may need some auxiliary variables to be introduced. The fourth type of constraint that we could have are called preference or soft constraints. Things like we could have constraints stating red is better than green. They are often representable by a cost for each variable assignment. As I was telling you, binary constraint satisfaction problem is one in which each constraint relates at most 2 variables. We could create a constraint graph where nodes correspond to variables and arc corresponds to constraints. Coming back to the map coloring problem here, we had 7 constraints, 1, 2, 3, 4, 5, 6, 7, and we could draw a constraint graph here to represent relation between the variables on the constraint graph. Each of the nodes corresponding to the variables. General purpose constraint satisfaction problems use the graph structure to speed up search. We will look at this in one of our lectures. While we are talking of higher order constraints, let us focus our attention on a very interesting cryptarithmetic puzzle. Cryptarithmetic puzzles are puzzles where you write things in letters and operate using mathematical operators and expect that each letter, if it stands for distinct digit, we can find some substitution for the letters in terms of the digits such that the sum is arithmetically correct, with the added restriction here that this leading letter should not have a 0. When we are trying to solve such problems, we can see that this small problem of saying 2 plus 2 is 4, we have 6 variable constraints for the above example. This literally means that all 6 letters that we can think of, T, W, O, R, U and F, are together in a constraint. And the constraint is that all of them needs to be a different digit. The addition constraints on the 4 columns of this puzzle, 1, 2, 3, 4. The 4 columns of this puzzle, they also involve several variables. All of these create a higher order constraint and they could be represented in a constraint hypergraph. So, here is the cryptarithmetic puzzle 2 plus 2, 4. On your right is the hypergraph. We could see that the 6 variables F, T, U, W, R and O are all together constraint, and this C1, C2, C3 are the carryovers possible at these columns. So, when we want to solve them, this could be like 6 placeholders, and I could have 4 placeholders for the answer, and I could have these placeholders for the carries. And the constraint hypergraph for this problem shows both the digit constraints as well as the column addition constraints. The constraint that all of them needs to be different digit is coming from this square box, and the constraint that F and C3, if this is the carryover C1, carryover C2 and carryover C3, if you remember, this was F. So, the constraint between F and C3 is coming here. C3 and F have a constraint. Similarly, and C2 as well as O here have a constraint. So, T, C2 and O have a constraint, so on and so forth. So, the constraint hypergraph for the cryptarithmetic problem shows the digit constraints as well as the column addition constraints, and each constraint is a square box connected to the variable it constrains. So, how do you look for solutions under such problems? Under standard search formulation, we can start with a basic naive approach and then improve it. States are defined by the values assigned so far. So, we could have the initial state given by the empty assignment, and then a successor function like assign a value to an unassigned variable that does not conflict could be defined as a successor function, and the goal test could be if the current assignment is complete. Now, we should note that this is same for all CSPs. Every solution appears at depth n with n variables. Path is irrelevant, so can also use complete state formulation. And for a domain of size d, we have a branching factor b of n minus l into d at depth l. So, that leads to factorial n into d to the power n leaves, and this is a huge space to search. Could we do better than this? So, we can look for a specialized version of depth first search. CSPs are solved by this, and the search is called backtracking search. The key intuition is that we build up to a solution by searching through the space of partial assignments. Order in which we assign the variables does not matter. Eventually, they all have to be assigned. If during the process of building up a solution, we falsify a constraint, we realize that this cannot be on the part of the solution. So, we can immediately reject all possible ways of extending the current partial assignment and backtrack. Backtracking search is the basic uninformed algorithm for solving constraint satisfaction problems. We look at one variable at a time. So, variable assignments are commutative, no fixed ordering is there, only need to consider assignments to a single variable at each step. And the second idea is to check for constraints as we go about. That is, we consider only values which do not conflict with the previous assignment. For that, we might have to do some computation to check the constraints, but then we get one step at a time towards the goal. Here is the backtracking search algorithm. The only thing I want to focus here or point you out is the idea of selecting the unassigned variable. We have a routine to select the unassigned variable. That is done in a way that no constraints are violated. Is used for a depth first search, values for one variable at a time, and backtracks when no legal values are left to be assigned. So, let us look at our 4 queens problem and try to understand backtracking search. So, here is the 4 cross 4 grid, and we start with placing our queen at this location. So, from the constraints that we have placed ourselves, that no 2 queens should attack each other, we know that this is not a legal position for the second queen, this is not a legal position for the second queen, but the third position on the second row is a legal position for the second queen. So, we put the second queen here and move one step further to look for a solution for the third row. This is no longer a legal position, this is not a legal position, this is no longer a legal position, neither is this a legal position. So, what we have realized at this point is that after we have assigned the second queen, we are not left with any legal position for the third queen. We have to backtrack. So, we remember what we started with, backtrack and get a new position for our second queen. With the new position for the second queen, we start once again with the third row to place our third queen. The first position is not legal because we have a queen here which will attack, but the second position is a legal position. Therefore, we move forward and look for the fourth row. So, we cannot have a queen here, neither we can have a queen here, nor a queen at the third position, nor at the fourth on the fourth row. That means, after we have assigned this queen, we are not left with any legal positions in the next step. So, we have to abandon this path and backtrack. So, we backtrack, and now where do we backtrack? We need to understand that we have already looked at all possibilities for the second queen given the first queen. So, we must backtrack to starting with another position for the first queen. So, we backtrack to a point where we put our first queen on the second column, then we have the queen here, the third row We could have a legal position at this. Given these 3 queens, we could get a legal position for our 4th queen. So that's our solution. So that's how backtracking search works. Let me repeat this very quickly one more time. So we had some legal positions up to this level, and when we tried for the 3rd level, we could not have a legal position. So we backtracked and started with an alternative in the 2nd position. We could have a 3rd position very nicely, but we could not have a 4th position placed. But then we have realized that we have exhausted all possibilities of our 1st queen itself, and therefore backtrack to removing our 1st queen to a different position. And once we had done this, we could arrive at a solution. So plain backtracking, as you have realized, is an uninformed algorithm. We do not expect it to be very effective for large problems. We remedied the poor performance of uninformed search algorithms in our previous discussion of state space search by supplying them with domain specific heuristic functions derived from our knowledge of the problem. But because constraint satisfaction problems have in themselves some structure or representation, we can solve CSPs efficiently without such domain specific knowledge. General purpose methods that address the following questions improve backtracking search. A. Which variables should be assigned next, and in what order should these variables be tried? B. What are the implications of the current variable assignment for the other unassigned variables? C. When a path fails, a state is reached in which a variable has no legal values, can the search avoid repeating this failure in the subsequent paths? General purpose methods can give huge gains in speed and in improvement of backtracking search. Ordering which variable should be assigned next, in what order should its values be tried, or filtering, can we detect inevitable failures early, or structure, can we take advantage of the problem structure. These can lead to improving backtracking search. Let us now look at the variable and value ordering heuristics. The backtracking algorithm contains a call to select the unassigned variable, and it simply selects the next unassigned variable in the order given by the list of variables. Now this static ordering would seldom result in efficient search. Therefore, the idea is to choose variables with the fewest legal values. Let us try to understand this with the help of our map coloring example. So on your right, we have the map coloring problem with 7 variables. Let us say after the assignment of WA to red, we assign NT as green. Now there is only one value possible for SA here, and that's blue. So it makes sense to assign blue here rather than assigning the value for Q. This is what the minimum remaining value heuristic does. Now it has also been called the most constrained variable or the fail fast heuristic, because it picks up a variable that is most likely to cause a failure soon, thereby pruning the search tree. The minimum remaining value heuristic does not help at all in choosing what would be the first region to color in our map coloring problem, because all of these 7 variables, when we start, can be colored in any one of red, blue or green. Now this is where the degree heuristic comes in handy. The degree heuristic lets us to choose a variable with the most constraints on remaining variables, and it does attempts to reduce the branching factor by choosing the variable that is involved in the largest number of constraints on other unassigned variables. For the map coloring problem, if you look at the 7 variables, SA is the variable with the highest degree, which is 1, 2, 3, 4 and 5. The other variables have degree either 2 or 3, except TA here, which has a degree 0. So we choose the variable with the most constraints on the remaining variable, that is, we first choose SA, and thereafter we choose NT, and so on and so forth. Applying the degree heuristic actually solves the problem without any false step. If we keep on choosing the consistent color at each choice point, we can still arrive at a solution with no backtracking. These two heuristics that we have discussed, actually we are looking at which variable to select. But then once a variable is selected, the algorithm must decide on the order in which to examine the values of the variable. This is where the least constraining value heuristic comes into play. The least constraining value heuristic allows us to choose the variable that rules out the fewest values in the remaining variables. Coming back to our map coloring example, let us see that after a partial assignment of red and green to WA and NT respectively, what is our choice for Q? We could now choose to color Q either blue or red. But we need to understand that blue is a bad choice, because it would then eliminate the only legal value possible for SA. So the least constraining value heuristic prefers to color Q red rather than coloring it blue. So far our search algorithms that we have considered, the constraints on them only looked at the variable when it is chosen. It would be a good idea to look at some of the constraints earlier in the search or even before the search has started. This can then drastically reduce the search space. Let us look at one such idea called the forward checking. The forward checking keeps track of the remaining legal values for any unassigned variable, and then it terminates search if any value has no legal values to color from. So let us look at this map coloring example to understand forward checking. Here on your right is the constraint graph, and we have 7 variables as we have been discussing. To start with, all these variables could be colored in any one of the 3 colors. Now let us say that we have colored WA red. When WA is colored red, then the variable NT and the variable SA, the only legal colors left for them is green blue. And now if we color Q as green, then the only legal values left for NT and SA is blue, whereas NS could be colored red and blue. After we have now decided to color V as blue, we see that we are left with no legal colors for SA, and the search must thus terminate. The forward check propagates information but does not provide early detection for all failures, as we will see when we look at this newer idea of constraint propagation. Constraint propagation propagates the implications of a constraint onto the variable, other variables, to detect inconsistency. So continuing with our map coloring example, we initially have all three colors for each of the 7 variables. Now, after we color WA red, the only legal values left for NT and SA is green and blue. At that point, if we color Q green, the legal values that's possible for NT and SA is blue, but because we are propagating this information locally from one variable onto other variables, we now immediately realize that NT and SA cannot both be blue together, and therefore we know we will not be left with a solution, a path to a solution, if we carry forward our coloring this way. So constraint propagation repeatedly enforces constraints locally and could detect failure early. We will look at a cryptic arithmetic puzzle in order to do this. So here is a puzzle which says send plus more is equal to money. As I had told you earlier, I could think of placeholders for S, E, and D, and I could have placeholders for M, O, R, and E, on which I will put my guess of digits between 0 and 9, and then I would have placeholders for M, O, N, E, and Y. And then, as discussed earlier, we have carryovers 1, 2, 3, and 4, which we call C1, C2, C3, and C4. And we create a placeholder table where the guess for M, O, S, R, Y, D, E, N, the 3 plus 3, 6, 7, 8 variables that I have to identify, is to be recorded. Now, the first thing that I must realize in this problem to be solved as constraint satisfaction is that here only search will not give me a solution. I have to do some reasoning along with the search, and when I am doing this, I have to think of taking the constraints forward. When I am making a guess, I make a guess and then take this constraint forward and see if it violates or conflicts. If it violates or conflicts, then I should come back and do a search again for another value for that variable. So to start with, we should realize that here C4 should be 1, because the carryover can be either 1 or 0, but a cryptic arithmetic puzzle requires that the first placeholder is not a 0, therefore C4 must be 1, and in that case I have M equal to 1. So my first answer of getting to a constraint being satisfied is the fact that the constraint between C4 and M gives me an answer that M is equal to 1. Given M is equal to 1, I update my table by putting 1 here and putting 1 again in a place where M is occurring. So I put a 1 there, and next I focus on looking for an answer to either the second column or the third column. So if I focus on the second column, I could see that I have a constraint between C3, S, and O. M already is known to me to be 1. and it is required that I have to carry forward a 1. So the number here would be 10 or something more than 10. So my initial guess could be that let that be a 0. That means O is a 0 in the sense that this is 10. So I start with O being 0 and take O equal to 0 and put zeros in these placeholders 0 and 0. Given O equal to 0, I then have a interesting relationship that I need to understand. Third column here. I have E here and I have N here, and this is a 0, and we should realize that E plus N, there must be some relation. The En is a pair, and I should realize that N cannot be 0 even if En is a pair, because already 0 is taken by O, and the En pair, for E to be different than N, C2 must be at least 1. Otherwise, if C2 is 0, E plus 0 is actually E, so E and N will be the same number. That gives me a very interesting realization that the carry forward C2 is 1. Once I realize the carry forward C2 is 1, I then take one step further and assume C3 to be 0. Once I take C3 to be 0, I have then S plus 1 is equal to 10, because that's a carryover. So S plus 1 is equal to 10 gives me S is equal to 9. So I have my third variable satisfied, S equal to 9. I update my variables, S equal to 9 there, and then now I have to look for R, E, N, D and Y. So I focus on my fourth column and I realize that N plus R must be E plus 10, because I need to carry over 1 there. So this value that I get in my fourth column must not be E alone, but E plus 10, then only I can carry over C2. So I write that N plus R is equal to 10 plus E, and already from here, my third column, I know the fact that E plus 1 is equal to N. Given these two, I can substitute E plus 1 for N here, and then I will have R equal to 9. But the moment I have R equal to 9, I realize that S is already 9, so there is a conflict. At that point of time, C1 comes to my rescue. So I say C1 is actually not 0 but 1. If C1 is 1, then I have C1 plus N plus R is equal to 10 plus E. So this one is like plus 1 here. 1 plus N plus R is equal to 10 plus E. In that case, R will come out as 8 and it does not have a conflict. So I update this C1 as 1 and I realize R is 8. So put my 8 value there. Now it is interesting to note that I have a relation between E and N already there as a pair, but my last column also makes it clear that there is a relation between D and E. But only thing that I must realize is that the Y that I have is actually the relationship that D plus E is equal to 10 plus Y, because I have a carry of 1 here. So once we look at this, then I know that D plus E is 10 plus Y, but we know that Y cannot be 0 because 0 is already taken by O here. So D plus E is not equal to 10, neither is D plus E equal to 11, because if d plus e is equal to 11, y is equal to 1, but we already know m is equal to 1, so there would be a conflict. So the only possibility at this point of time is that d plus e is equal to 12. If d plus e is equal to 12, then y is equal to 2. With y equal to 2, I already have a carryover 1, so that's pretty good. So this is what I populate my placeholder with, y equal to 2. So now all I have is to find out the values for d, e and n. Now it is interesting to note that I know e plus 1 is n, and from here I know that d plus e is 12. D plus e could be 12 for digits 0 to 9 in a number of ways. One could be that I could start with d equal to 3, but if I start with d equal to 3, I would have e equal to 9, but s is already 9, so d equal to 3 is not a possibility. Then I could start with d equal to 4, but if I take d equal to 4, e would be equal to 8, in which case it would conflict with r equal to 8, so d is not 4. Then I start with d equal to 5. I could see that if I take d equal to 5, I will have e equal to 7. This is satisfied, no conflict. But then let me check what happens if I have e equal to 7. E equal to 7 would mean that n is equal to 8, in which case it will conflict with r. Therefore, I have a realization that actually d is not 5 but 7, and I have d equal to 7, in which case e is equal to 5 and n is equal to 6. So I could populate these numbers there, and now I have all the variables satisfied, none of the constraints violated. And if you add them now, I have 7 plus 5 12, 2 carry over 1, 6 plus 1 7, plus 8 15, 5 carry over 1, 5 plus 1 6, and then 9 plus 1 10, 0, carry over 1 and 1. So this is the solution for the crypto arithmetic puzzle, sand plus more equal to money, with these values for the different letters. What one needs to understand here is that when this puzzle was being solved, we had done search and reasoning intermingled. It is not that I was only searching and trying to satisfy constraints. Searching was done to satisfy constraints, but also what was being done was that I was doing some amount of reasoning to understand what should be my next guess. So these type of things is what is usually done in constraint propagation. Constraint propagation is the general term for propagating the implications of a constraint on one variable onto other variables, and we want to do this fast. So it's no good if I want to reduce the amount of search, but if we spend more time propagating constraints than we would have spent doing a simple search, there is no point of propagating the constraint. So we want to have very fast propagation of constraints. A very fast method of constraint propagation that is substantially stronger than the forward checking that we have discussed today is arc consistency. Let us now try to understand the idea of how arc consistency provides a fast method of constraint propagation that is substantially stronger than forward checking. So here an arc refers to a directed arc in the constraint graph. An arc x to y is consistent if for every value Vx of x there is some value Vy for y. So let us say in our example of the map coloring, the current domains of SA and NSW are blue and red blue respectively. Given the current domains of SA and NSW, we could see that there is a consistent assignment for SA equal to blue. I could always pick up NSW equal to red, and I can therefore have a consistent assignment from SA to NSW. Whereas, if I am looking for arc consistency from NSW to SA, if I pick up red, I could have a legal value blue here, but if I pick up blue, I do not have a legal value in SA. Therefore, the arc from SA to NSW is consistent, whereas NSW to SA is not. All that the arc consistency tells me is that I have a consistent arc from SA to NSW. Arc consistency can be used as a look ahead to search for space reduction, and the idea is in two ways. Either we look for full arc consistency look ahead, or we look for directed arc consistency look ahead. The full arc consistency look ahead is about considering all pairs of future variables and then removing values from one domain for which a consistent value in the other domain does not exist. The directional arc consistency look ahead is about considering only directional arc for the future variable. Like in the example that we were discussing for the map coloring problem, SA to NSW, the arc is a directional arc consistency. Arcs that become inconsistent could be made consistent by deleting the inconsistent values. Like if here we think of making arc consistency, we can think of deleting certain value from NSW, that's the value blue, and we would end up having consistency from NSW to SA. But the problem is, if I delete a value from some variable's domain, a new inconsistency could arise in arcs pointing to that variable. So arc consistency must be applied repeatedly until no more inconsistencies remain. This is what we will try to understand in this example here. So on your right is the constraint graph. Let us assume the current domains that we have for the different variables NT, SA, V and NSW as shown. So as you can see, there is consistency from SA to NSW, because for a value from SA I can pick up a value from NSW, but the other way it's not correct. So I can delete the blue value, and then what I will have is a consistent arc between NSW and SA. But then if we have realized this, earlier the arc between V and NSW was consistent, but because of deletion of blue, if I now pick up red this side, I will have inconsistency because I will have no legal value for NSW available. And therefore, to maintain arc consistency, I need to delete red from here. And then I have enforced arc consistency between NSW and V one more time. This has to be applied repeatedly until I have no more inconsistencies in the constraint graph. Now, if you look at these two domains of NT and SA, if I somehow apply arc consistency between them, then I would need to delete blue from NT in order to have arc consistency between SA and NT. So enforcing arc consistency from the arc from NT to SA would make the domain of NT empty. And this is how arc consistency could detect failures earlier than forward checking. Now we will focus our attention in a couple of backtracking strategies. We will walk through two important backtrackings. The chronological backtracking is the simplest of them. It's about going back to the latest choice point and try another choice when a partial solution cannot be extended. So here is what the chronological backtracking does. We look at this through our 4 queens problem. So we place our first queen, and then the only possibility is here now to place it either in the third or in the fourth column in the second row. So we place it here, and then we realize that we are not left with any legal choice for our third queen. According to chronological backtracking, we would now need to backtrack from here to the point where we could get the second choice. So we would backtrack from here, and we will look for using the other choice at this choice point, which enables us to have a legal value for our third queen. But if we go one step forward, we realize that now it is no longer possible to have any legal position for our fourth queen. So we would need to backtrack again, but that backtracking would be to the last choice point, which we have not yet exhausted. So this one is already exhausted, so we will go back here, and that would be chronological backtracking. This is something that we have also looked at when I was talking to you about the backtracking algorithm. Now we will look at one of a slight variance of this called the back jumping. So the back jumping, whenever we arrive at a dead end, it backs up to the most recent variable that illuminated a value in the current domain. So let us try to understand that with a 6 queens example. So here is our 6 cross 6 grid. Let us place our first queen in row 2. Then we place our second queen in row 5. And now the legal positions possible for our queen, we pick up one and place it in row 3. You should realize at this point that either I could place my fourth queen here or somewhere down there, here. So I take that option and place my fourth queen here. Now I am left with only one legal position for my fifth queen. I cannot place it here because this queen will be in direct attack. I cannot place it here, it will be attacked by this queen. I cannot place it here because this will be then attacked by the third queen. I have only possibility of placing it is in this position, and which is on the fourth row. Now I am looking for a position for the sixth queen. If I go for the first row, that's not a legal position because this queen will then attack. If I go for the second, this first queen will attack. If I go for the third row, I already have a queen sitting on the third row. I cannot use the fourth row, neither can I use the fifth or the sixth row. So I now do not have a legal move for my sixth queen. I do not know which position to place because I now have an empty domain. Now when I want to back up on this and go back I would rather love to go to the most recent variable that eliminated a value in the current domain. So how do I go about doing that is I try to look at the earliest queen that conflicts with the squares for the 6th queen. Like, let me see what I mean by this in the given example. So if I want to now place something in this square, I would love to identify which is the queen that conflicts with the square for the 6th queen. So if I do this, I realize that it is my 2nd queen sitting there, which is actually not allowing a queen in the 1st position on the 6th column. Next, if you look for the 2nd position, you see it is the 1st queen. So I try to identify the queens that do not allow me these positions and try to record each of the earliest ones. So the 3rd position is covered by the 3rd queen. The 4th position is covered by the 4th queen sitting here. So that's the earliest queen that conflicts with the square for the 6th queen. Then for the 5th square, I have the 2nd queen, and for the final, I have the 3rd queen. I record all these queens, the earliest of them, and then I take the largest of these values. The largest of these values actually gives me the latest variable that conflicts with making the current domain empty. So I take this value, which is 4, and now I know that if I have to jump back, changing 5 would not help. I have to go back and look for making changes at the variable level 4. This is back jumping. Now, back jumping works only when the dead end is encountered during search. That's sometimes called the leaf dead end. If by chance, if you go there and you are not able to get an alternate value at the culprit variable, in our case the 4th variable here itself, that's called an internal dead end. Beyond that point, back jumping only does chronological backtracking. Now we will look at one more variant of back jumping called the conflict directed back jumping. We will simply introduce the idea here, and working through an example, I leave it as an exercise for the readers. The conflict directed back jumping is an algorithm that is aware of the underlying constraint graph. It determines where to jump back to based on the actual conflict that it has recorded. So it uses an ordering on the constraints and identifies the earliest constraint that violates it, and it maintains a conflict set for each variable, that is list of previously assigned variables that are related by constraint. When we hit a dead end, it back jumps to the most recent variable in the conflict set. Interesting is that it learns from a conflict by updating the conflict set of the variable we jump to. When a contradiction occurs, conflict directed back jumping, which remembers the minimum set of variables from the conflict set that was responsible for the problem, and takes a decision. In fact, it saves no goods variables as new constraints. This is better than simple back jumping, which had no such memory. So to conclude, we had looked at constraint satisfaction problems, which are an alternate formulation of problem solving. Each problem is represented as set of variables, set of constraints, which together specify a relation on all the variables. Solution is a specification of the allowable values for the variables. We have confined our discussion to only finite CSPs. CSPs whose domains are finite sets. There are many interesting problems that have infinite or real domains. We have not looked at them. We have looked at backtracking, which is a depth first search with one variable assigned per node, and then we add to it consistency checking. Variable ordering and value selection heuristics, we have seen, help significantly. We have looked at the idea of forward checking that prevents assignments that guarantee later failure. And then we have looked at constraint propagation, including arc consistency, that does additional work to constrain values and detect inconsistencies. Thank you very much.